Hello, everybody. Yeah, welcome to the SAFO seminar. We have 2 more to go, including this one. And so I know a lot of people are getting ready for the holiday season, right, or conference seasons. And so it's good to have some interesting talks. And today we invited Dr. Suna Ni from University of Maryland. And I know because everyone is familiar with 2 very important fire events this year, right? One in early this year, that LA fire. It's probably one of the most devastating fires in the California history. And the second one, I think sometime in the summer, and there's a Canadian fire that caused a lot of pollutant transport in Minnesota. And I just learned yesterday from my postdoc, he said this is actually we hit a record for the worst weather air quality in the Minnesota history. Right? So the fire has significantly impacting our event daily life, especially with the climate change, you understand the frequency of fire increases quite a bit. So this prompts the invitation to our speaker today, and she's an expert in fire sciences. And when I was a graduate student, when I was applying for school in the US, I learned that there are only 2 schools that have a fire science department in the US, and University of Maryland is one of them, is the best one. Okay, so it's a lot of people working on specialized on fire and fire-related, interesting problems. So you received your PhD from Texas A&M in 2018, and has been pretty active in fire science. And Dr. Lee has, received a lot of grants recently on evaluating fire safety and understanding the building interaction with the fire and building materials, how that is important for fire spread. And I've seen some news report about your research as well. So with no further ado, I'll leave the stage for you.
Thank you so much. Yeah. Thank you so much for the introduction, and happy to be here to talking a little bit about my research in the wildland urban interface fires. So today I'm mainly talking about the structure burning and ignition burning and the collapse, and how the collapse impact the fire dynamics, and how the collapse impact the fire spread. So in the recent years, the vivid fire has become a bigger issue. This is mainly because of the climate change, and also because in the past few decades, there's a lot of structure building community was constructed in the interface between wildland and the urban area, which we call vivid area, WUI, wildland urban interface. So when we're talking wildfire is part of the ecosystem, and it's happened naturally, and because it's unable to avoid it, right? It's a part of ecosystem. It's good for the ecosystem as well. But the vivid fire, it's different from wildland urban interface fire, different from wildland fire. Wildland fire, it's mainly the vegetation, the fuel is the vegetation, the trees, the grasses, right? While when the fire comes to the community, it's a vivid fire, it involves both the natural and the human-made elements. There's some vegetation, and there's a lot of structures. So let's see the LA wildfire, so there's a lot of structure was burned. And the burning of those structures in reality accelerated the fire spread in those communities. And the rapid fire spread in those communities basically overwhelmed all of the firefighting efforts, because our firefighting is not designed for a community level, and it's mainly designed or supposed to fight a building fire, a single or a small neighborhood, rather than the whole community. Basically, there's no way to really, if a wildfire it comes to the community and a large spread, there's no way to extinguish it. And we hope the wind can stop it, so we can slow down the fire, or we can develop some fire barrier between different regions, so the fire does not spread over this fire barrier. This what we can do, stop the fire in our community if it happens. So the different from the wildland fire is part of nature system, and we also hope it's also in some ways good for our ecosystem. While vivid fire is different, it's leading to a lot of economical loss and structural damage. In reality, and the vivid fire problem can be engineered. That's why in the past few years, a lot of researchers, not just in fire science, And there's a lot of professor and colleague in civil engineering, in mechanical engineering, in the aerospace, steeper in this research field, try to address this problem together using the engineer methods.
So can you double check is your microphone turned on? Maybe just move it towards
More close. Yeah. Is it now better?
Is it good enough? Yeah. Okay, all right.
You can, now, okay. Now it's, yeah. So here's the picture, which is from the Maui wildfire 2023, and the fire was started in August, and almost damages a history town like Hana, right? But after the majority, a lot of part of this community was damaged. But in the photo, it show one building, and this, the red roof building, and this building is survived. So this. And people try to identify why this building can survive. If this building can survive, why we cannot, we can do some mitigation, or we can design this building to make all the building resistant to wildfire, right? So, and some research have shown that the main reason is the roof structure of this building is metal. It's a non-combustible material. And the area surrounding this house has relatively little vegetation compared to its neighbors. And it's also had a fewer opening for the ember to enter. So if you have large open and in the wind, for example, your wind using a relatively large mesh, so the ember can enter into the building, ignite the building. And this building that have less open, or most open is closed during the fire event. And also this building is recently, years it has some innovation, renovation, and which also improves the fire resistance. So by studying this type of structure, we can identify what type of building feature contribute to the fire resistance of the building. So when we design the building for the next wildfire, and we can make sure those buildings are more fire resistant compared to the older buildings. Well, here definitely I have one question. If you want to make a building resistant, the cost also increase, right? If you're talking to some local fire department, and their answer was the most important problem is the cost. So you definitely, there's mitigation to how to make your building very resistant. You can, in Australia, there's some building even install some outdoor sprinkler system, right? So when the fire comes and sprinkler system activity, the problem is that even indoor sprinkler system is unable to commonly use in the residential building in the United States. California, Maryland force you using the sprinkler system in residential building. So if you want to use in building the sprinkler system outside the door, so that would be even more expensive, very difficult to, be used for the whole community. So our mitigation should be, it need to be efficient. In the meantime, it should be, cost efficient. Well, definitely, when we're talking about the way we find mitigation solution, it's not just you make a structure, a building very resistant to fire. That it's a mitigation solution can include multiple different aspects. For example, prevention and preparedness, forecasting, detection, monitoring, and response and recovery. It's basically covers these three parts. So the efforts is not just from one part. It need to be working together to make sure we have good prevention and preparedness. For example, you training the people, residents there. So when you need evacuated, how you clean the vegetation in your building and prepare the building for wildfire. And forecasting, you need to have a very good simulation too. And data-driven, or the simulation need to have accuracy, but also forecasting, you also need to be in real time, right? And the detection monitoring, how to detect a wildfire very early. For example, you can using the drone to detect the wildfire according to the smoke or the temperature change. And then you need to transfer those data to the control center. While the response is how you respond, how the firefighting, if the fire already happened, how the firefighting activity should be deployed. And because our human firefighting is not designed to fighting a community level fire. So there's some research, for example, they develop some robots or some drone to carry the fire water ball to the site. There's a lot of research ongoing in this part as well. When the last part is recovery, because the from the loss of a VV fire and the loss is not just from the damage of the building, and which we call direct cost. A lot of cost is called indirect cost. So when the business was disrupted or interrupted by a wildfire, how long it takes the business recover, come back to this site. So there's a lot of so our goal is to make the recovery as fast as possible, but that's a lot of work need to be done. So basically, the mitigation solution for VV fire cover all these 5 parts, and there's a lot of efforts is ongoing, but I don't think there's a perfect solution for all the community, and those mitigation strategies should be different for different community. While my research is focused, because it's a big problem, and my research is just a little bit part of this problem. So my research focuses on what physics and environmental factor controls ignition and fire spread in dense VV neighborhoods. So how for example, the building's feature or the environmental feature, how that make one building more easy to be ignited or less combustible. And second part, how we can model, predict, and ultimately prevent structural loss in the future wildfire disaster. For example, we study the different type of window system to see which one can prevent under the window is basically the opening. Once the window is broke up, you open an opening. So that is easy, let the ember to enter in the building. So we study the different type of window system to see which type of window system is the best one for VV fire scenarios. And the last part is how do we develop the fragility curve for structure in VV community. So fragility curve is basically to tell you this is the level of fire hazards and what's the probability of this building at the different damage levels. And we develop this fragility curve currently mainly based on the survey data. But the survey data, you have a lot of missing data on the data, maybe for different buildings, it's not completed. So we also will leverage the simulation and experimental data. So that's the 3 part of my work. We cover simulation, not too much, and experiments, and most of my work is experiments. And also I have some background in risk modeling. And recently we get a project from the Joint Fire Program to evaluate a different risk framework for the VV community fire scenarios. So the first part of my work is talking a little bit about one NSF project which try to explore the feasibility of using high-resolution CFD-based simulation to model the structure burning and the interstructure fire spread. And the high fidelity, it's the high resolution, not high fidelity. So this model we mainly using the software we use is the fire dynamic simulator, which is the software designed by the NIST. It's very specifically for the fire research, and it's definitely LES and CFD based. Well, the reason we want to develop this high-resolution model, which can model a structure burn, is because the experimental test to burning one structure is very expensive and time-consuming. And we can just study a couple different type of scenario. We cannot using the experiments to explore the different type of building configuration. You have different roof system, you have different siding material, decking material, window system, right? So there's no way for you to do all this type of tests to tell me which to optimize your building design. So we want to using the FDS as a tool to see whether the FDS can model the structure burning well. Most current FDS simulation focus on compartment fire or external fire. For example, it's, let's say, unenclosed fire. So the compartment fire is, for example, if this room, I have a fire in that corner, how the fire will spread in this room, right? And from the initial stage to flash over to the decay phase. So this is a compartment fire. It does not involve the enclosure itself. While the pool fire, let's say, unenclosed fire, you have a pool fire, and let's see how the flame was developed, temperature developed, heat flux, radiation. While the structure burning is a little bit different. The structure burning, for example, a structure was ignited by wildfire, which is from outside to inside, right? And if the ember was entered in building and ignited one furniture in the building, and the fire started as a compartment fire. And then when the flash over, and because most residential in US is a timber structure, so and then it's involved a whole the enclosure, and then become a large external fire. So there's some transition from a compartment fire to a large external fire, right? So this is FDS never done for this purpose. So this the research for this project is try to evaluate whether it can do this type of work. So we want to evaluate whether the existing FDS technique can replicate the structure burning, and whether it can replicate the ignition of a nearby structure which is caused by a burning structure. And ultimately, the goal, we want to see what's if it will work, and we develop a simulation framework. So people can use this to design your structure. So you change the different configuration of your structure and in the simulation to see whether the structure will be burned, will be ignited, and whether it will burn to the ground, right? So it's used as a performance-based design tool, and also used as a risk assessment tool. If it does not work, at least we identify some knowledge gap. I think, according to the current research outcome, it can do a reasonable job, but the accuracy or some small phenomena we are unable to capture. So there's a lot of work need to be done to make FDS able to capture the burning of a whole structure. So the structure we selected for replicate is the two buildings in the Maui wildfire, and this one is a source structure which was burned in the wildfire, and the burning of this structure was ignited as a one-story building. And the reason we selected this neighborhoods is because we have the data for there's some camera recording the whole burning process of these two buildings, so we can use it to calibrate or to evaluate our models. And if you can see the two buildings, the space of these two buildings, there's some trees, there's some vegetation. And this vegetation impact a lot the fire spread from the right building to the left building. Well, also in the simulation computation domain, we're including another structure, which is just to bring additional, to consider the potential turbulence caused by this additional structure. So here is a video can show you the burning process of these two structures. I speed up, that's why the fire spread very fast. So it started as a compartment fire. The fire spread, ignited external fire spread the compartment as the first story, and spread to the second story, and ultimately it involves the whole building's enclosure because it's a wood frame construction, so the structure itself is very combustible. And then the wind changes, the wind at one moment the wind changes its direction and shift the direction to the one-story building and ignite the vegetation between the two buildings, and together those leading to the fire, the burning of the next building. And ultimately, both buildings was burned down to ground. Yeah, that's a video, shared by a fire department. So here is some detailed timeline for the building. So if the fire started at the time 0, it's from the backyard, and then it's ignited the interior, the first story, some room in the first story, and spread horizontally. And then the fire spread vertically as well. And ultimately, in this time, basically the whole building is began to involve in fire. And ultimately, the whole building was involved, and in the location, we identify the next ignition time of the next building. It's very difficult to, for sure to tell you when it's ignited. Our estimation is at this range is the next building was ignited, and in particularly, you can see something already impinging to this target walls. And ultimately, the both structure was burned to the ground. So that's the whole fire spread process for these two buildings. And this building, the reason also we selected this area is because this building, the one-story building, this building is ignited by flame impinging rather than the ember. Because FDS currently is unable to simulate the ember generation. And so that's why we try to avoid the ember problem in this simulation. So here, this slide show you how we modeling the burning behavior of the source structure. Is a two-story, the red one source structure. So we can, in RAR, we can develop a very high fidelity model. For example, we can develop the model and we apply the pyrolysis model for different type of construction material. So we heated and the material start from the pyrolysis process and emitted a lot of combustible gas. And then meet the oxygen and the burning happens, right? We can simulate this process, but it's very high fidelity. And the computation cost is very expensive. That's why we try to simplify the model. Rather start to define the material pyrolysis, and we calculate the fire load in each room, and we know the fire load, and we also count the fire load from the enclosure because the wall is wood walls, so we consider the different fire load. And then we assign this fire load as a burner to the enclosure of the building, and we consider the fire for the in the different story, and also we consider the fire load in the roof and overhang. Here, in the first story, there's an overhang here. So we try to consider the different part. So we apply those fire load as a burner at the surface. For this burner, and then we define according to the fire curve, the calculation of the fire curve, and we can figure out what's the heat release curve. There's some, there's some simplified equation to help us. Here is the fire load and how the fire will be developed. And there's a growth phase, and a stable phase, and come to the decay phase. So definitely, originally, those model is designed for compartment fire. It's not for a large external fire. But there's some, it's not perfectly matched very well, but we want to see how it works. So we figure out the different regions, the fire burners, the HR curve, and then uniform distributed the fire heat release curve to those enclosure and to see how it works. And we investigate two different types of configuration of the burner. In one configuration, we apply the burner to all the entire height of each story. But in the other one, we apply it to just half of the height of each story. And we also model the vegetation. While the vegetation model, we're using a relative high fidelity model. We consider the material start from the timber, start from the wood, the foliage, or the leaf we consider as wood material. And we are using, in reality, the wood is the plumer tree, which is relatively popular in Lahaina. While we're unable to find the material pyrolysis model for this type of tree, but in FDS validation example, there's a Douglas form pyrolysis. And usually the pyrolysis model for different materials, there's no bigger difference. But maybe the ignition temperature some are different. So we're using the Douglas firm's pyrolysis data to define each particle. And the tree was modeled as a lot of particles. And those particles represent the funnel or branch and those leaves. And then apply the material pyrolysis model. So once you define the material pyrolysis model, basically it's a chemical reaction, a multiple-step chemical reaction. So that's how we model the tree model. And this model is not developed by ourselves. We're using, in FDS validation examples, they're already using the similar technique to model the burning of couple tree and validated by their experimental data, and it works very well. And we also, definitely we need to include in the wind. If you can see the video, there's some shift of the wind. And the wind data we got is from the NCER's, the weather research forecasting model. They have a regional wind data, but the resolution is 100 meter and the time resolution is 15 minutes. So it's pretty large compared to our simulation. The good part is that we found the location, which is the nearest great point, is pretty close to this testing site. So that's the good part. And also we apply the time varying wind as a velocity boundary condition in the FDS. And also the wind profile was applied at the interlat to represent the boundary layer and providing the vertical shear needed for turbulence development. So here's some simulation results to show you the tree burning. So in the time, 774 seconds, at that moment, that's the point the tree has not been burned, but the wind already shifted the directions. And because the wind pushes the flame and to impinging the tree, so ultimately ignited the tree. So the tree was ignited in 87 seconds. And we can simulate it. So in our model, we are able to simulate the ignition of the tree and when the wind shifts its direction, which is consistent with the video observations. And so here I show you a couple comparison about our simulation. And so basically we can simulate those critical events, how the tree was burned and the flame changes their direction, the fire developed, but overall the fire size in the model is a little bit smaller than the video. Another thing is the camera capture, the information captured by the camera does not, because of smoke, everything, it's not present as a real fire size. So there's some inconsistency as well. So in this model and the target structure, the burning, when the simulation was stopped, when we figure out at the point when the target wall was ignited. And once the target wall ignited, we didn't simulate the fast spread of this structure, and which is our current work. So we basically replicate the burning of this structure, and then to see whether the burning of this structure can ignite the next building. That's the start of interstructure fast spread. And there's some, the ignition time. Here's this slide shows some ignition time compared to the video observation. So the ignition time is, so basically, we monitor the target wall, the one-story building's temperature, surface temperature, and incident heat flux. And we put a lot of sensors there, and then we calculated the average temperature, and we also check the maximum temperature history as well. And we get the results from the two different type of burner configuration. And we found that usually in most scenarios, full burner, the heat flux and the temperature from the half-full burner, and it's much higher, not much, it's higher than the full burner configurations. And also we found that the fire was basically started very dramatically. Well, the heat flux, the reason is because here is, the fire is even in the burner setup, at the beginning, the fire is it's a growth phase, a steady phase, and decay phase. So when that's the burning of the source structure, well, what we here is the response or the thermal response of the target wall, which is this is a target wall. And we both found that no matter you're using the half-wall burner configuration or full-wall burner configuration, and we can see a rapid increase in the surface temperature or the incident heat flux at 750 seconds, and the value becomes stabilized at started stabilize at 1,100 seconds, and then as the fire grows further, and it's definitely will decay ultimately. So here's when you try to figure out when the target wall was ignited, and you have to have some ignition criteria, and which usually we using the ignition temperature for the materials. So for the one-story building, the target wall here, it's using the plywood. So the plywood's ignition temperature is vary a lot. And it also depends whether the ignition is a piloted ignition or auto ignition. So auto ignition, there's no any spark there, right? So if I was using a candle to ignite the wood, it's called a pilot ignition. But if I just heated, then nothing touches the surface, it's called pilot ignition. While usually the pilot ignition have relatively low ignition temperature. For plywood, it's ranged to from 290 degrees to 390 degrees C, while auto ignition temperature is 475 to 620 degrees C. And if this is large ignition and we don't know what's the exactly ignition temperature for the wood used for this building, right? So if based on this different ignition temperature, and we can identify the different prediction ignition timing. So we basically monitor the temperature of the surface, and we compare to the ignition temperature of the material itself, and we to identify when the ignition of this target wall happens, right? So because the large range of the ignition temperature, so the predicted ignition time is also have relatively large. But if we using the 390 degrees C, it's also a value recommended by SFP. So if we're using this number, and the half-wall predicted ignition temperature is 1,785 seconds, if for the full wall configuration, its ignition temperature is ignition time is 1,827 seconds. And in reality, we also do a lot of sensitivity study and what impacts the ignition time. And we found that it's very sensitive to your surface emissivity, because that's impact what's the radiation it can receive. Surface emissivity, and also impacts by the sensitive to thermal conductivity of your target wall material, not just the ignition temperature, right? So what's the ignition time? It depends a lot of parameter, which give us, highlight that when you do this type of simulation, you want to simulate the ignition and the spread, the timing of the spread or ignition and the spread well, you need to have a very good quantified or characterized material properties, because it's if your material have relative high ignition temperature, and the ignition time can be delayed significantly. So, and from the video, our observed ignition timing is basically 1,781 seconds to 1,893 seconds. And if you compare the predicted ignition time based on the temperature criteria 390 degrees C, and our prediction is falling within this range. So that's some about the comparison between the ignition timing, between the video observation and our predictions. And here I can show you the simulation. I didn't include the smoke. If I include the smoke, the frame cannot see very clearly. So in this picture, I did include smoke, and it's based on the full half-wall configuration, and that's the time when the target was ignited. And I also compared to the video observation at the two potential ignition time. The fire definitely is, here the fire looks small. It's because it's how the FDS visualizes their frame. In reality, here there's also a lot of frame as well. It depends how you visualize your frames. So here we also study a little bit about the interaction between wind and vegetation effectors. So at the time 1774 seconds, the wind changes its direction. So it directs the frame towards the trees. So, and then the tree was ignited in 1783 seconds. So, which basically, and the vegetation ignition ultimately was caused a very sharp heat flux. So that's the strong spike. At this point, basically, the tree was burned, and because the tree is so close to the target wall, so the target wall was exposed to a large heat flux. That's the spike. And also, we compare the scenarios. That's why in the mitigation strategy for wildfire, VV structure, you have to clean the vegetation around your structure, and you make sure the space between the structure is enough. So, well, and the problem, what we found is that, and we compare if the tree is not there, and we also compare the scenario. If the tree is not there, and this is the no tree, this is those blue one, and the orange one, right? I compare the different average heat flux and maximum heat flux. And what we found is that if there's no tree and the spark is relatively small compared to the image in the last plot, well, that's the heat flux. If you compare the no tree and with the tree scenario, the spark is much smaller if there's no tree. But the problem is that we found that in those non-spark periods, and the tree there, and it has some benefits because your tree there, the radiation from the burning structure will be blocked in some way. But once the tree was burned, anything you have a large radiation, there's something in the middle. It always broke some radiation. That's why in the non-spark area and in those periods and the no tree scenario even have a larger heat flux. But once the tree was burned, the tree itself generates a lot of heat flux, and then the structure will begin to burn. So that's how it does not mean you should have some tree be there to block the heat flux, because once it's ignited, and it's accelerates the fire spread significantly. So and our prediction time based on the temperature criteria 390 degrees C, and which is 1,785 seconds. It's very consistent with the direction shift of the wind and the burning of the vegetation. So let's see, if there's no tree there, there's no wind direction change, and the next building possibly will not be ignited. This happens to this data building. So the two building is here, the one-story building is here. In reality, there's another building, one-story building, and that building was not burned. And the report said it's mainly because the wind is in this direction. So when the one-story building was ignited, and the wind changed direction again, and it's burned back to the two-story building. That's why the next one-story building next to it was not burned. And also some people was analyzed. The reason the red roof structure was survived is maybe because it's lucky enough. the wind changes the direction. It's also possible, but we don't have the data to analyzing how the wind changes when the fire next to this building. So here I'm talking a little bit of the current limitation of the current modeling. And if we look at the two-story building burning, and we can observe the structure collapse during the whole process. So when the structure collapses, it changes the fire dynamics significantly and also changes the spread. So for example, you have, when partial of the structure collapse, it basically generates a large opening. And this large opening changes the ventilation condition significantly. And also, a part of the structure spread. And let's say if the first story is able to contain the fire, and then it can prevent the fire spread from one story to another. But your floor system collapse, right? And once it's collapsed, it's definitely your compartmentalization was failed. So it's accelerated the fire spread. So while current FDS is unable to incorporate the structure collapse, because the structure collapse is a lot is related to the mechanics, right? You find an element to simulate it how the structure, or you figure out a simple way to activate the structure collapse. So the kind of model is unable to capture the structure collapse. So it's also unable to capture the impact of structure collapse on the fire dynamics. And also, in our simulation, we basically put the burner on the enclosure directly, and all the burning is from the enclosure. But if you look at the video, the fire started as a compartment fire, right? A room fire first, and then spread inside the building, and then involves the whole structure. So the FDS is unable to, the transition, and we are unable to simulate it. But you can definitely put your burner inside, and then to put some burner in your enclosure. That's something we are trying, working on it to see whether we can simulate the transition of a fire from a compartment fire, a room fire, to involve a whole building the fire. And also, this model, the structure burning in reality, it generates a lot of embers, and because it's a wood structure and it's modeling, and the small particle was generated from this burning. While FDS cannot simulate the ember generation for burning structure component, there's some empirical equation based experiment data and relate to the heat release to the ember flux, right? But that's for the vegetation, not for structure burning. So, and also this morning I talking with Doc Hong's postdoctor, because there's a lot of turbulence and the structure collapse process. For example, structure component attached from a building, and it's broke up. And this process also generates embers. When it's fall to the ground, it's an impact to the ground. It's also generates embers. And when the burning timber on the surface, on the ground was impacted by some foreign object, it also generates embers. So it's not a simple relation. It's very difficult to just, it's not the ember generation rate. It's not just a simple function about heat flux. It should include more component. But the kind of model in our field is mainly to connect the ember flux with the heat release rate. That's based on a couple experimental data, not a very comprehensive experimental data. And that's some, yeah. So based on our simulation, and we found that the reason we stop our simulation at the ignition point is also because we are unable to predict the structure collapse. Once the structure collapses, the fire becomes very intense. Because unable to simulate this pattern, we definitely unable to simulate the fire dynamics. So that's why we design some small experiments which try to see what's the fire-induced collapse or timber structure and its impact on fire dynamics. That's the next part I want to introduce. Here's some brief introduction to show you how the fire impacts the structure collapse. And when the temperature increases, it basically causes the wood to char. It loses its strength and stiffness, and it's reducing the load bearing capacity of a timber member. and ultimately leading to the structure collapse. And also the connection of each structure component will also failed. It can be nailed, but the nail also will be is steel, right? Under high temperatures, the nail also will fail, right? So that's the connection degradation also accelerates the loss of structure integrity. And also the uneven burning creates the differential deformation and the instability, and also the failure of key member triggers the load redistribution and the progressive collapse. Here show you an image, a couple images is how a structure was the wood frame construction, the light wood frame construction, the most common construction type, structure type for residential building in the US. So that's how the fire was developed, and this definitely, and this building, it has some wind. So that's why the collapse was in one direction. And ultimately, the fire originally was contained, and then when the collapse happens, after that, the fire basically intensifies significantly. And if I have another building here, it's very possible. It's once it's lateral collapse, it's a lot of space between these two structures was occupied by the burning structure, and it may reduce the efficiently space distance between the structure, which can accelerate the fire spread. So, and also the structure collapse also has some impact on fire dynamics. For example, it's create a new opening, partial of your wall was filled. It's basically open a large opening, right? And this increases the oxygen supply and it also release the hot gas. And it also bridges the compartments. I have some wall between the two rooms, and now this wall and it prevents the fire spread from this room to another room. Now the wall was collapsed, and it's basically accelerates the fire spread, no matter horizontally or vertically. Let's see the ceiling field, and it accelerates the fire spread in vertical direction. And also it's redistribute the fuel, and expose the fresh combustible fuel surface to heat flux. So because when the structure component collapsed and its location was changed, right? And the burning structure member ignited the unburning surface, and it exposes the fresh combustible material to heat flux. And it's also produced a sudden airflow surge, and which intensify burning and triggers reframing. Let's see, if I'm not sure you may already have some experience with barbecue, right? So when the char was burning and you try to make the burning more intense, and you can move the char a little bit so that the burning will be more intense. Similarly, mechanism, and also when one structure was burned, when this structure collapsed, and it's impact the nearby structure, which accelerates the fire spread, which I already covered in the last slide. And it also increases the amber generation and lofting, and enhances the long distance fire spread. And that's I have one slide to cover why this happens, and that's my explanation. Possibly something is not 100% correct. Happy to hear any comment. So this is what we observed from all the previous fire incidents, and we thought there's some coupled interaction between fire dynamics and the structure collapse. While most counter research is I either study fire dynamics, I assume the structure never collapses, and how the fire developed, right? Or I study the structure behave under the fire, and I never thought when even my structure have some deformation, if the bottom is burning and my floor system have a large deformation, and it's become more close to the fire source because the deformation is downwards, right? It makes the distance between the structure and the fire source also more enclosed. So but in counter research, the two phenomena most study is studied separately. I only study the fire dynamics, or I only study how the structure was behave under relative consistent fires. But in reality, the two have a lot of interaction with each other, and the fire impact the structure. how your structural response and also your structure collapse impact your fire dynamics. So our experiments try to investigate the collapse behavior, timber structure and the fire, and also to understand how the structure collapse influences the subsequent fire dynamics. We do a couple skilled tests. We will want to design some skilled structure, but my colleague told me, design a skilled structure is a lot of component. It's very expensive as well, time consuming. Home Deposit have a lot of doghouse, give us the perfect size. We want to scale down a room by 1/3, 1 to 3, right? But the doghouse give us very similar dimension we need, and also timber structure. And the structure type of doghouse is different from wood frame construction. Wood frame have a lot of small wood studs, right? And that's how they constructed. But if you look at some single family structure, residential building, and next to this building, there's always have some shed structure which is used as a storage purpose, right? And those structure type is very close to the doghouse structure. So we get the doghouse from Home Deposit, and in the original products, it only have a large opening at the front surface. But we want to make it more realistic, more like a building. So we created some opening at all the other side walls, and the rear wall and the side walls. And in the tester, and we basically put a external wood creeper fire. We simulate the fire under the structure behave under an external fire. So we have two wood creeper. The outside one, we simulate the vegetation burning. And we also put some wood creeper inside the compartment to simulate the internal burning. Let's see the fuel from the fire load from the content furniture and a coach and a table and so on. So we ignited the fire at the outside and to see how the fire was spread from outside to inside. And we put the wood creep at the different location of the structure to see how it changes the spread mechanism. So that's the goal. And we also consider the window. The window, we have considered the different seal height. The seal height is for the floor surface to the window bottom, right? And we test a different seal height. And another thing that another variable we test, we include in those column base, or we don't include column base. If you look at the residential building in the US, some do have column base. And in reality, in vivid air, and there's a lot of dry leaf accumulated at those bottom, and which makes those structures very vulnerable to wildfire. That's why if you look at the codes, how to prepare your structure for building, and they recommended remove all the dry vegetation at the bottom. So that's why in some tests, we include in the column base, and some tests we remove the column base. So this is the test setup in our own burning room, and this is a test matrix. And we're using the camera to recording the fire development in different angle, and also we're using the loader cell to measure how the mass loss. Based on the mass loss, we can calculate the heat release rate. And in reality, our burning room is able to capture, when you have the hood, and those hood can collect all the burning products. It can calculate the heat release. But the problem is the fire for this one is we have two hoods. One is 1.5 megawatts fire. The fire can be up 1 to 5 more megawatts. It's almost a 6 feet by 6 feet compartment fire, a pretty large fire. There's another hood, only 600 kilowatts, 600 kilowatts. It's relatively small. And our fire size is something in the middle. Our large hood is unable to capture the heat release directly. So that's why we rather using the hood to help us to calculate heat release. We're using the load cell to measure the mass loss, so we can calculate the heat release. Once you have mass loss, you can multiply by the heat of combustion of the material. Most of the material is pine wood, right? So you can get the heat release. So here's a couple of burning video. Can show you. This is the first. The left one is The left one is the front fire exposure, and we put the wood creep in the front walls. And this one is the burning, which is the wood creep under the real walls, the back walls. So, and if you can see the fire spread for the front fire scenario is spread from the external burning and ignites the internal wood creep directly, and then the fire will develop very fastly in the structure, inside the structure, and involves the whole structure, ultimate collapse. But if you look at the real world, different because the window is relatively small, so the fire was unable to spread directly to the room. And it's ignited the wall first, and the wall was outside the surface of the wall was burned first, and then the wall was burned through to inside, and when the wall inside was burned, and then ultimately the burning of the wall ignited the internal wood creep. So that's why, you know, if your building have smaller opening, and it's help you to protect your building in maybe fire scenarios. The code required, even for the ventilation, when vents, you have to using some mesh, right? They have some requirements of the mesh size, but that is mainly try to prevent the ember to enter into the building. But for opening, you know, if your window have small size, that also help a lot. That's the test we done during the past summer. So here's basically a summary about the burning process. This is the frontal fire scenarios. It's basically the burning of the wood creeper directly ignited. It's directly ignited the internal wood creeper and ultimately involves the burning of the whole structures. And ultimately, the structure was collapsed. Well, the next slide shows you the burning process when the fire, the external wood creep at the real wall or the back walls. It's basically the burning of external wood creep ignited the wall first, and then the walls, because the wood still have some thickness, right? So the wood burns from outside to inside. It takes a little bit of time. And when the interior surface of the wood was burned and ultimately ignited the wood creep inside the compartment, and then the burning is developed very fast, and it's ignited the whole building. Ultimately, the structure was collapsed. So that's the two different burning process we have observed in our scaled out test. And we also, according to the mass loss, and we also calculated the heat release. As I mentioned, you multiply the mass loss by heat combustion of the material pine wood, and then you can get the heat release. It's approximated because our roof material, some part of our roof material is also combustible. So, but the majority material is pine wood. That's why we consider most of mass loss is come from the burning of the timber. So, and we get the heat release curve, which is the blue dashed line. And we found there's two different patterns, and one, in sometimes it only have single peak, and in another test have a double peak. The reason is because the single peak is corresponding, the fire spread to the external burning of wood creeper directly ignited the internal wood creeper. So the burning is relatively smooth and continuously. That's why you can only see a single peak when the internal wood was burned. While the double peak is the scenario when the fire was at the real wall or the side wall, at the window side, right? The opening is relatively small. So it's unable to ignite the internal wood creeper directly. So the external wood creeper burn and then almost extinguish, right? Well, at this time, the wall is already being ignited, right? But the wood, it takes time to ignite from outside to inside, right? So, and then when the internal wood was burned, and the wall interior surface was burned, and it ignited the internal wood creep, and which leading to another peak. So this is corresponding single peak and double peak corresponding to the different progress, fire spread progress. And here's some
Quick interruption. How many slides you have?
I think two or three, I think. Yeah, very fast.
Yeah, just want to make sure I have enough time for it.
Sure. So we also we observe the different collapse directions and the inward collapse, outward and lateral collapse. Because our building is pretty symmetric, right? Once the fire spread ignited internal the creep, it's become a compartment fire. And its fire is mainly come from the majority damage of the building is because the burning of the internal the creep. So, and our building is pretty symmetrical. That's why most collapse inward. In reality, for any firefighting or fire spread in VV area, that's a good scenario because once you outward spread, you basically occupied some space between the two structures. You reduce the efficient distance between the two structures and accelerate the building. And we found that most outward spread collapse or lateral spread and the structure collapse in one side, to one side, and up from those scenario with the column base. The reason is because the column base under the fire, it was damaged in not uniform. So the four column and maybe one is more damaged compared to the other. That's why it's leading to some collapse in one or have some preference in the collapse directions. So here's some what we observe about ember generation. And we found that in the moment of the structure collapse, and basically we can find a burst of ember. So that we observe a lot of ember, and I didn't put the IR image, which is more clearly. You can see, before the collapse, after the collapse, before the collapse and during the collapse, that a lot of ember was generated. And here's some reason why ember was more ember generated. Because your foreign ember fragment release ember as they separated. And once it's upon ground impact, and this fragment generate another burst of ember. And the impact will further break up, partially burns timber on the ground. It's also the impact load, from the foreign objects. It's also impact the burning timber on the ground. It also can generate some embers. And also the increased ventilation accelerates the ember ignition potential as well. There's some also the aerodynamics disturbance, which enhances the ember lofting and enhances the plume-driven transporter, boosts the long-range spread. So that's my explanation about why we observe a lot of ember during the collapse procedure. If in a community, if a structure collapses, and it's collapsed in one direction, and it's occupied the space between the two buildings, and it's already accelerated fire spread. And then it generates a lot of ember. And those ember can spread a very long distance, right? It impacts and accelerates the spread of fire significantly. That's why we needed to include in the collapse into the consideration about the fire spread among the structure in the VV community. Here's a summary. So basically, a brief summary, maybe not very brief. So the FDS simulation, it can reproduce the interstructure fire spread with the burner configuration and including the correct, if we can include in the correct wind field and burning of vegetation. While ignition temperature is remain highly sensitive to the ignition temperature. What's a material ignition temperature? Ignition temperature is a material property, and emissivity and thermoconductivity of the raw material, and which means we need to have a relative accurate material property inputs in the VV modeling. And further improved simulation accuracy require the accurate capture of the transition from a compartment fire to fully enclosure environment. And we also needed to include in the structure collapse and the feedback on fire dynamics. Because the collapse including a lot of mechanisms which can intensify your burning and also intensify your ember generations. And we also needed to, and we also needed to consider how we design a building to make sure the structure more resistant under the fire. And there was even it collapsing right away or in the right relatively good direction. So and also when we consider with fire and with Sprd, we have to consider the winter direction shifter, external fire exposure, interior fire development, structure burning, and structure detail. And all this together is to control the heat exposure fire dynamics, collapse behavior, and the subsequent fire spread between the structures. So here's the project, part of the research is funded by one NSL project, and this is my students in my group. Yeah.
Thank you so much.
Thank you.